Okay, we're 10 o'clock. Okay, I'm 12 noon time for Central Time. Okay, we will get started. Any questions so far? Let me see. Any question for
I
your? Yeah, go
I
ahead.
I actually do have a question. For the final project, do we
Yes.
have to use Flex and YAML, or can we build our own scanner? So like
Well,
instead,
whatever.
well, okay,
It's an open project. We do not require any tool or anything. It's on your proposal, whatever you propose or whatever you want to do.
okay,
And you can also modify your proposal. It's an open project. So the goal is there's only one goal. One goal is put whatever you learn from this course into the project, right? That's our only goal. And whatever you can think of related to programming language and you have learned from this course, you can put on the project. Okay.
okay,
But that's only guideline we have. Okay. But we do not limit you to use language. Say you want to write it in JavaScript, it's okay. Nobody care, right? As long as it's related to programming language.
Mhm.
And you do know that what you are doing is related to this course, that should be fine.
All right,
Yeah.
thank you.
Any other question? Okay, no question. We will go through the topic we have this week. Okay, just like previous week. But again, we don't have that enough time to go over the detail for everything. If you need a detail, you pretty much need to look at the pre-recorded video. So the purpose of this one still be give you the overview of this chapter and give you the incentive of why we do something here. Okay, as a main purpose. So today we are on lecture 13, week 13, abstract syntax tree. So we finished the tree, okay, because the parsing translate the so-called token string. We actually tokenize in the lexical analyzer part and then build a syntax tree by the parser, right? So this chapter we are talking about from the parser to the evaluation of the tree. Okay. So we build a tree called abstract syntax tree, AST. Okay. Abstract syntax tree, AST. So your whole program now is in this AST. But now we want to evaluate this tree. Evaluate. Okay. And then by the evaluation, you know the grammar, whether grammar is correct or not, right? Second, you will be able to start to generate, prepare to generate the code, the Taki code. Okay. So that's the purpose of this lecture, and then you need to learn attribute grammar and evaluation of attributes, and what is action routine. Okay. And then the syntax tree declaration for the purpose of evaluation. Okay. And then how to generate the parsers and combinators. Okay. And also Python library related to the parsing. Okay. These are the topics we will talk about today. Okay. So basically, we are assuming that we already had the AST. Okay. Now we are doing this and this to making sure that actually the program is correct for the grammar. Okay, for the grammar, and also prepare to generate the code for the next stage. Okay, and then first one is the idea of attribute grammar. Okay, attribute grammar. So attribute grammar is a new term. So it's not context-free grammar. Context-free grammar is the one that we describe the grammar for parsing. Okay. Attribute grammar is from the AST, we decorate more things to it for the evaluation. Okay. So both the semantic analysis Okay, semantic analysis is for the purpose of semantic analysis, and intermediate code generation can be described in some sort of annotation or declaration. And this declaration, we call it attribute grammar. Okay, and attribute grammar provide a formal framework. So it's actually a framework for declaration such a tree. So this is what it say here: the annotation and declaration of parsing tree. That is attribute grammar. Okay, and attribute grammar is one framework. Okay, formal framework for it. The note below discuss attribute grammar and later Eha Cousins action routine. So action routine is one kind of attribute grammar. Okay, and it's used in many processes. Okay. Okay, let's keep going. And then attribute grammar, we start with the declaration of the tree, then consider the syntax tree. Okay, consider the LR parser. Okay, LR parser. Basically, here we are talking about LR parser. Why LR parser? Okay, let's actually go back to the previous chapter. Let's go back to the previous chapter, that's chapter 12. Okay. And let's look at the LR parser. So in previous chapter, we do talk about LR parser. Then LR parser has a here. Okay. So LR parser has a table in it. It has an action and go to. These are related to the action routine. Okay. These are related to the action routine. We'll look at this later. Okay. The relationship of this one later. But actually LR parser have this precompiled table that's related to what we are talking about here, the action routine. Okay, the action routine we talked about in previous slides. Okay. Okay, let's continue. Okay, for example, left-hand side is our so-called context-free grammar. Okay, and this one actually we do have these. So if the value of the expression equals the evaluation, the value of the expression plus the terminal. Okay, so what this one means is actually if we have a expression, say I'm sorry, there's an expression. Okay, there's an expression, and then it actually is equal to 3 plus 4 plus 10 plus 10. Okay, let's assume that. Okay, so this one is an expression. This one is a terminal. The terminal's value and the expression value plus the sum, it will equal to the value of the expression. Since this whole thing is an expression, so this expression is equal to one expression plus a terminal, right? Probably a term. Is that okay? So this end result of this expression, the whole thing, will be the expression's value plus this term's value. Okay? So left-hand side is our context-free grammar. Right-hand side here, this one is the so-called attribute grammar. And this one is for the declaration. Since we evaluated tree already, so here we will have this expression to help the evaluation of the tree. Is that okay? Does that make sense? This is what we talk about here. Okay, I'm sorry. I actually don't know which page it is. Let me go back, okay? This is what we talk about here, attribute grammar. And attribute grammar's purpose is to declare a tree. And so that is the format of the attribute grammar, okay? How we formulate attribute grammar. So basically we want to declare a tree, okay? And attribute grammar define the semantics of the programs. What is semantics? Semantics is the evaluation. So basically it is expression's value. The expression actually can derive as the expression plus a term, right? So we do have the expression of 3 plus 4. This one is this expression, right? Plus 10. Okay, this 10 is the term, right? So this whole thing is a expression, and it's this expression. So the evaluation of this whole thing is described as what we just see here. The one we just actually, where it is here, okay? It actually described in this way, okay? Okay, that's what it is, okay? So basically the context-free grammar is like this, okay? You actually, no matter what language it is, it has the expression equals expression plus term, whatever, okay? This is the whole grammar we have. So the grammar will generate properly a form, the constant, whatever, okay? This additional expression. So this, okay, whatever. This is the context-free grammar, okay? And button up. And then, okay, let's look at it. So this one's attribute grammar will be like this. So left-hand side is our context-free grammar. And then right-hand side is based on the evaluation. So evaluation of the term 2 and the terminal's value. And then their sum will be the E1's value. Is that okay? Mm-hmm. So E2's value plus the T's value will be the sum will be the value of the E1. Okay. So the second rule, E2's value and the T's values difference will be the E1's value. So basically the whole thing actually been described with the attribute grammar like this, okay? And then what is the relationship with this one as the syntax tree? It is like this. So in the syntax tree, we have expression 1. It is equal to the sum of the expression 2 and the terminal, right? So we declare what? We declare the E1 equals the sum of the E2 and the T. Declare this attribute grammar on this node. So when we actually evaluate down to here, the value of this one and the value of this one will be helping to evaluate the sum of the value of this one. Is that okay? So every term has its own evaluation. Maybe this one term equals some factors value, you know, and this one E2 may be also sum of some E3 and some E4's value, whatever. Okay, so they will get some value for E2 and then pass up to here and then get evaluated for this one. Is that okay? So it's a button-up operation. It is a button-up operation here. Okay. Okay, so that's the relationship of this one. So when we build this with this attribute grammar, then we can evaluate a tree from the button and go up based on this. So it's very important. Okay. First one, you need to have this context-free grammar and then build the AST. So there's a tree. and each node of them got decorated with this attribute grammar. And then eventually you can evaluate a tree. Okay, eventually you can evaluate a tree. So each one of these say, okay, I forget to talk about it. Each one of these E1 is an attribute. It's actually called attribute. This is also an attribute. This is also, so this is a value. It's actually a variable. Theta value is available, the terminal's value. So terminal may have many variables. It's not only one. Value is only one of it. It only may also have error or some other attribute. Okay. Value is only one attribute. It's not the whole complete attribute. It have many attributes. Every non-terminal term or terminal term, they have different attributes. Okay. So in strict definition of attribute grammar, copy rules, and the semantic function call. Okay. So basically, what is semantic function call? This sum is a semantic function. Okay. It is semantical function. So this one is a function. Okay. Semantical function. Okay. So function call to the two kinds of possible. Okay. Whatever. Okay. Okay, so basically, this one talk about the rule. Okay. Okay, it should be okay. It's not. Here is a lot of detail you can read. Okay, Okay, so attribute grammar for an ID. Okay, a reference to information about it in the simple table. Okay, so if you are a ID, so you have a X variable. Okay, it got assigned equals A plus B. Okay, so X is a ID, A is also ID, B is also ID. So basically, for this ID, the reference information about it is in the simple table. Okay, simple table, we have a simple table in the parser for this X, A, B, okay, whatever, okay. And it actually has some value associated with, so for example, memory. So basically here in the syntax tree, X equals A plus B, okay. So basically this link to here, this link to here, this X also link to here, okay. If a simple table has some value or something, you will link to that. This is what it says. ID has a reference. So ID have a reference. So for ID, if you are not a expression, then the single ID say constant. Constant has its own value and is stored in the simple table. Okay. So for example, you have A equals 3. That's constant value is in the table. Okay. That's what it say here. Okay. Anyway, there's a lot of detail. Okay. So second is for an expression. So if expression, it may have a attribute called type. Okay. So here, attribute grammar, as I say, they may be an attribute called value. Okay. There may be an attribute called reference. And reference is going to the simple table. And there may be an attribute called type. So this type may be double type, right? Or maybe it's actually integer type. Okay, whatever. So there are several attributes, not only one. Okay, not only one. So there are other things, and even error will be included. So error, why error? Because your expression has error. Okay, here your lower have error. Lower have error, you pass the error up. So basically this program has an error. Okay, so semantic error is also an attribute. If your lower level has some error, you also have the error, you pass up. For any internal node, there's a list of semantic error. Okay, So basically during the process, each term of here is one attribute in the attribute grammar framework. Okay. And how to evaluate is another issue, but here you just remember each node is not only the value type. Okay, value is one of the type of the attribute, but there are many type of the attribute here. Okay. So attribute grammar is a special form of content-free grammar. Okay, whatever we already describe it. Okay. And each attribute have well-defined domain, such as a value. It may be integer. Okay, value is very simple. It may be integer, double, floating point, character or string or expression. Okay, attribute grammar is a medium to provide a semantic for content-free grammar. So content-free grammar by itself do not have semantics. Okay, we don't evaluate on it. So this one is contribute semantics. So we try to attach the attributes to the content-free grammar syntax tree. Okay. Okay, so this one we talked about it already. So semantic attributes may be assigned to their value from their domain at the time of passing. So the passing and when the evaluation time, we will assign to it. Okay, based on the way the attributes get their value, they can be broken into two types. Okay, so now we are going to define the type of attribute. There are two types of attribute. One is called syntactic synthesized attribute. The other one is called inherited attribute. So these two types, very, very important. Okay. One is inherited attribute. So there are many attributes, and one type is called synthesized attribute. The other one is called inherited attribute. Okay. So let's look at it. So attribute grammar carries some semantic information along the parallel tree, okay? And it's useful for static semantic specification and static semantic checking. Okay, here it says static, okay. So what does this static really mean? Anybody know? Versus dynamic. Anybody know?
Type?
Hmm?
Your type? Declaration?
No. Static here means the compile time. So when we say dynamic, it actually is at the runtime. So when you run the program, there is a different type of evaluation, right? Runtime, you have different type of evaluation. So such as integer, okay, C equal A divided by B. Right here, we talk about semantic evaluation. It's just based on this value to evaluate. At runtime, the B may be 0. So you will have division by 0 problem, but it will be detected only at the runtime. We call it dynamic error. It's not static error. Is that okay? Is that okay? So that B equals 0, you evaluate and we get an error of division by 0. But we cannot know it when we compile it. So the syntax tree evaluation, this is fine. But when we run it, we run into the trouble getting the division by 0. That's a runtime problem. Is that okay? So attribute grammar can only evaluate the static semantic checking, not a dynamic one. Does that make sense? Any question? Okay, give you an example. Okay, let me try to use Java to explain it. Okay. Okay, let's actually create a dynamic. Okay. Okay, so let's have a integer a equals 3, integer b equals 0, integer c equals a divided by b. Okay, and then we print the print c. Okay, this is a simple program. So compile, nothing wrong. Compile, nothing wrong because whatever syntax tree we build, this program is just okay, right? This program is just okay. But if we actually run it, and then we do get some error. Okay, it has this one Java arithmetic exception. Okay, so something wrong. We don't get a result. Okay, we don't get a result. We don't get a result because this one, it actually say this one. Okay, the division by 0 happened. So this one is detected at the wrong time. We call it dynamic. But here we talk about attribute grammar. When we do compile, it actually pass, no syntax error. Okay, so that's the difference. So right here, that's the difference between the dynamic and static. Okay, so here we talk about attribute grammar. It can only detect the static error. Okay, it cannot detect the dynamic error. So dynamic error had to be found at the wrong time. So attribute grammar. Okay, these are some symbols. Okay, we're going to here, attribute grammar. Okay, attribute grammar is written in mathematical format. Okay, it's actually a set of these. It actually has a set of the attribute values. Okay, and then each production rule has a set of the function that define the attribute. Production rule is protection rule talking about these are protection rules. Okay. Left hand side, these are protection rules. How each data being generated, that's actually the protection rules. Okay. And each protection rule has a set of function, that's a right hand side function. Okay. Each protection rule has a set of predicate checking for the attribute consistency. Okay. And whatever these are, okay. So now synthesize attribute. So synthesize attribute are these. Okay, so you have x0 that's actually can be produced by s1 to sn. Okay, so the synthesized value of this left hand side value is a function of the right hand side attributes value. Okay, this is called synthesized value. So synthesized value actually is a expression from a expression plus terminal. This is a synthesized attribute. Okay, so the value of the x is determined by the children. Okay, the value of this one is determined by the value of the children. This is called synthesized value. So it's purely button up is called synthesized attribute. Okay, any question? Now let's look at the inherited attribute. So inherited the attribute is okay. The attribute of some term is determined by the value of itself, a value of its parent and siblings. Okay, so sibling is actually to the left of the tree, sibling to the left of the tree. So the value of a certain xj is, you do have x0 is the parent, okay, and actually it's derived some x1 to xn. In the middle, there's a value of xj. So xj's attribute is determined by its siblings and its parents. If there is some kind of the attribute that is determined in this way, we call it inherited attribute because it gets the attribute from its parent, right? Then we call it inherited attribute. So when will this happen? This will happen when we have, let's assume that we do have a double in the Java, okay? Double x equals a plus b plus c. So let's assume that we do declare a is a double, b is an integer, c actually is another double. So we do have a double plus integer plus double. So this term originally is integer, but it will be converted to double before it do summation. So the type of this term is determined by its parents and sibling. And the type of this one is a inherited attribute. Is that okay?
Mm-hmm.
So the type, that type attribute, but the value is different. Value of the B still coming from where? Value of B still coming from is sum. Is that okay? Is that okay? Value of B still coming from is sum. So B may be an expression. Right there, I'm using so B may be equals C plus D plus F. And then B actually is from C, A. Okay, so the type of this one will be determined by its sibling and parents. Okay, but the value may still come from the child. So synthesized attribute and the inherited attribute, okay, there are two types of attribute, but this one may be for type, and the value may be for the value maybe is synthesized. Okay, so you have to check different attribute. Value and type may be different. Okay, so here we are trying to talk about. Here it's actually purely math. Okay, so if I don't give you the example, it's very hard to understand. Okay, anyway, so the attributes get a value from its child. Okay, something like this. So the value of the sum coming from ABC. Okay, clicking from the attribute. So this one is synthesized attribute. Synthesized attribute also call it as a S-type attribute. Okay, synthesized attribute is also called S attribute. Okay. Inherited attribute, okay, we do have this one. So A get the value from S. This one actually is called synthesized attribute. A get the value from SBC. B get the attribute from the SAC. Okay, whatever this is called synthesized attribute. Inherited attribute. So expansion, okay, non-terminal expansion to terminal. So this one you have, if you go from up to down, that actually called expansion. fallback is called reduction. Okay. So reduction means that you get a value here, get a value here. You are going to evaluate this one. You get a value here, and you're going to do this one. Okay. Expansion means that, okay, I have an expression. I need to expand to a plus b, e times e. Okay. And then this e need to expand to e plus e. Okay. That's called expansion. Reduction. Okay. The reduction is actually button up. Okay. And then the value of this one value is coming from a constant phi. Okay. So the type of the value is integer. The value is coming from here. Okay. So there are two attributes. These two are attributes. So here we have a tree for 2 times 6 plus 4n. Okay. And the evaluation tree is like this. Okay. So the coming from a digit constant 2 and a digit constant 6 and digit constant 4. Okay. And then this digit constant 2 is a f of a factor. So factor's value is 2. And then term's value is 2. Okay. And term's value is this one times this one. So it's got a value of 12. Okay. So this is the decorated evaluation tree. Okay. So the tree, each term has its value. So term is here, and its attribute co-value is equal 12. Okay. So we do have a tree, and each one of them has attribute. So here we are evaluating the whole value system. Okay. But there are also other attributes such as type or error. Okay. And this one is SSD. Okay. SDD. Okay. Syntax directed definition. This one is called SDD. Okay, whatever. This one is syntax, and this is called attribute SDT. Okay. S attribute SDT. So here, S is a synthesized attribute. Okay. Now we have another one called L attribute SDT. L attribute SDT is for the inherited type. Okay. So L attribute SDT is non-terminal, can get a value from its parent and whatever node. Okay. This is called L attribute SDT. So all of the S attribute SDT can be included by the L attribute SDT. So L attribute SDT is a bigger family. Okay. You go difference left to right passing grammar. Okay. Okay, now next one we go into the evaluation the attributes. So evaluating the attributes, it's very simple attribute grammar. Okay, each symbol has its attribute. Okay, and they are synthesized attribute and the inherited attribute. Okay. So evaluate them, the process of evaluating the attribute is called annotation. So when you start to do evaluation, it's called annotation or declaration. Okay. So basically, when you evaluate, you will call on a semantic function. Sum is a semantic function. Okay. Okay, well, basically, when you evaluate, it's a simple expression, 1 plus 3 times 2. Okay, it's passing trees like this. Okay, it's passing trees, passing like this. So when we do evaluation, we do bottom up. So constant 1 is the value, and then pass up to the factor. Factor pass up to the term. Term pass up to the expression. Okay, so this is passing tree like that. Same thing here, pass up, pass up. So up to here, you have the expression plus turn equals 4. So that's the expression here. And then pass up to the vector to turn, okay, constant 2, okay, constant 2 pass up. There's a time. So 2 pass up to a turn and then expression. Final turn for expression is 8. Okay. And this one apparently is mostly S attribute. Okay. But anyway, that's actually evaluation attribute. Okay, so top-down counter-free grammar, we build up counter-free grammar and to the syntax tree like this. And then we decorate each one with the value, okay, and you will be able to do evaluation. Okay, next one actually is the how to decorate the L attribute, okay, L attribute. So let's look at the example. So now this L attribute is not only the value, okay. So there is st, okay. Let me see. So here you have a expression, okay, and then there's a constant, okay, and then there's a expression tail, okay. So it actually is this actually is let's see, it actually is here you have a value of, let's see. So you have a constant 9. So you pass this 9 to the expression tail. So I think it has 9 minus 4. So you get the value of constant 9. Okay. It passed to the expression tail. Okay. So expression tail got a 9, right? And here you do have 9. Okay. So 9 minus 4 become 5. So this is 5 passed to the expression tail. So there's another minus, okay, and 3. So this one is a 5. So 5 passed down to here is 5 minus 3. You pass down 2 to the tail. And the tail now is an empty string, no more. So 2 got passed back. Okay. So ST is the what? Subtotal. This ST here is subtotal. Subtotal means the left-hand side values total. Is that okay? You do have 9 minus 4 minus 3. And its left-hand side subtotal is actually an attribute. It actually is an attribute. Is that okay? This is called L attribute. So your same passing tree can be decorated with S attribute or L attribute. If you decorate its L attribute, it's something like this. Is that okay? Does that make sense? Any question? Okay. So ST is subtotal from the left-hand side. Okay. When you evaluate this node, you have depend on its parent and its sibling. So this one apparently you get it from sibling. That's actually called L attribute. Okay. When your value getting from your sibling or your parent, that's called L attribute. Does that make sense? Any question? No? No question? No question, we'll move on, okay? So basically, there are two types of attribute, okay? And the ST is called subtotal, okay? So when you write your attribute grammar, you can write it in S attribute or L attribute, okay? And up to you, okay? Up to you. So here we describe the expression now in L attribute type, okay? Okay, anyway, so you do have two type of attribute you can write, okay? And no matter which type, you can actually, when we evaluate, you have to follow the flow. You need to follow the flow. That's called attribute flow. When you evaluate, you have to follow the flow. It's called attribute flow. Either it's going bottom up, okay, or top down, okay. You have to determine which, so it's top down is ALL, okay. So here we have declaration of top down passing tree, okay. So tons of subtotal, okay.
And why would I choose top down or bottom up?
It actually depends on many things, your grammar and also efficiency of the compiler. It depends. Okay, it actually depends. And efficiency and time, and also sometimes, okay, sometimes L attribute AC is more flexible. It covers more, okay. But it's not as natural as the bottom up, okay. It's not as natural as like that. And some attribute like type, usually L attribute is better. Like type, usually L attribute is better. Okay.
Like with the bottom up that you use a
Bottom up for value
stack.
more. Yeah.
Like that you use a stack and then you pop out the last expression.
Yes. It's easier, but usually for value. But type, usually you inherit from the parents. Okay. So it actually depends on which attribute we are talking about. Okay, so basically, evaluate the S attribute, you always evaluate your right-hand side value and then sum up, right? Evaluate your inherited value, you actually need to go top down, okay? Okay, right here is the description for L, non-L, and how it can be evaluated, okay? Now, actually, okay. So now come to here, attribute flow, okay? So basically, we do know about there are two types of attribute, but in reality, there's one more thing we need to learn that's called attribute flow. So attribute flow is how you evaluate your value. So you evaluate value, you basically use your production rule and the action. Action is the action routine, okay? So S attribute or L attribute, we call it action routine, okay? And we also need to have one algorithm called attribute flow to evaluate the attributes. So these are three things required, okay? So let's assume that we do have a production rule. E actually is terminal and terminal tail, okay? So your subtotal of the terminal tail will be assigned as T's value. So your subtotal is assigned from the T value. Is that okay? This is L attribute. So your subtotal, your TT's subtotal is coming from T's value. Is that okay? A plus B. So this one's plus C. The subtotal from A will be the value, T's value, TT subtotal. Your B subtotal is coming from A's value. Is that okay? Any question here? This is the first one, okay? So something like that. So this is a production rule defining the function code. So if you want to evaluate the subtotal for this one, you need to get the value from this one, okay? So if you want to get the TT2's subtotal, it is the sum of the TT1 plus T's value. Okay. So TT2's subtotal is the sum of these two. Does that make sense? Is that okay? And you carry to here. Okay. So this one actually tell you when you have a function call. This one's subtotal will be depending on these two values. So you get the value from these two. Okay, this production will determine how your attribute get values. Okay, does that make sense? So the attribute flow algorithm propagate attribute value. Your propagation of the value is going from left to right, and then subtotal going back to expression eventually. Okay. So this is called attribute flow. Okay, and this one apparently is for L attributes. Okay, and if you have the S attribute, is the value going from bottom up, but this one is L attributes evaluation flow. Okay, so that's attribute flow. So attribute flow give you the order how each value got processed. Okay, it's called translation scheme. So basically, we have such two types of evaluation, okay? And then we have several types of compiler, one-pass compiler, multiple-pass compiler, low and go compiler, and Archimedean compiler, okay? One-pass compiler means that we just go through the evaluation flow once, okay? Compile and everything got done. Multiple pass, you may do syntax tree generation first, attribute declaration, and then multiple passes. Okay. So one-pass compiler means that you a compiler that interleave syntax analysis and code generation, and in one pass, we call it one-pass compiler. Okay. And one-pass compiler is simpler and more straightforward, but it cannot handle the complicated grammar. Okay. Okay, so you have bottom-up and top-down attribute grammar to build a syntax tree. There are several types. Okay, depending on your attribute. Okay, this portion we don't go to the detail of grammar. Okay, that's too much. So you can do top-down using S attribute. You can also do bottom-up for L attribute. Okay, up to you, up to your compiler. Okay, more detail. Only 1+3 times 2. You can do many type of the attribute declaration. Okay, so we don't go into the detail for this. Action routine. Okay, action routine. So action routine is a action function. Okay. So this is a way to implement the action grammar. Okay. So this one is one kind of the implementation for action grammar called action routine. Okay. So action routine is a syntax analyzer called attributes evaluator. Okay. And based on such document. So most production rules will use ADHA, handwritten translate scheme. Okay. So action routine are semantic functions. So you write your attribute grammar into functions. Okay, and your LL parser, okay, your action routine appear anywhere within the right-hand side. Okay, so S attribute will become function, semantic function of the certain sum or difference of the right-hand side. Okay. So that's F function. So implementation mechanism is very simple. When it predicts a production, the parser push all of the right-hand side into step. Yes. So this one show you is actually pushed to the step. So your value of the t is 3, right? Times, and then your e is 4. So later this one pop up and go back to get a function, and it's 7 for a e later. Okay. So this one is using stack, okay, for the action routine. So here we write this one top-down action routine, okay, that is. And recursive descent and action routine. So you can evaluate the tree using recursive descent as well. Okay, the grammar is like this, okay. So that is LL. If you do bottom-up evaluation, then LR parser generator, okay, is used. And there's a bottom-up evaluation if you do S attribute, okay. It very simple, okay. So bottom-up S attribute is very simple. So top-down parser with L attribute grammar, okay, and bottom-up parser with S attribute. These are naturally born. So syntax tree declaration. So if you have a language, okay, let's assume that we do have calculator language here, okay. So program equals statement list. Statement list equals statement list and declare, and or statement list with statement, okay, whatever, these are the definition. So declaration is declare integer, okay, and statement is this, okay, whatever, these are the grammar for a calculator. So this calculator language, okay, we have the context-free grammar, okay. So this is example we want to show. So this one is actually, if you have a program like this, you will create a syntax tree like this, okay, based on the grammar. And this one is undeclarated. So this one is undeclarated, but we will decorate it, okay. We are going to decorate it. So the grammar is written down as this one. Context-free grammar being rewritten as this one. But we haven't added the attribute grammar on it yet. So here is tree grammar. So here we have notation, okay. So tree grammar and context grammar a little bit different. A context grammar is meant to generate the language, okay. And tree grammar, we have a notation A column B on the left-hand side. Means that A is one variant for B, okay. So anyway, that context-free grammar, now we defining the term. So each node may have, each expression or non-terminal may have a name. These are attributes, type, simple table reference, okay, and error. These are some attributes to the node, okay. So each node, your tree generated, when we decorate it, you will be given at least these different attributes, okay. So simple table is inherited attribute. Error in is an inherited attribute, okay. Your location, error, and error out, these are synthesized attributes, okay. And this different attribute being shorthanded with EI. EI is error in, EO is error out, okay. And then S is a simple table, okay, something like that, okay. So we talk about this different attribute and its shorthand name, okay. Okay, and then okay, and then we do have this different node, okay. and each different node with different attribute. And then creating the attribute grammar for the calculator language. Okay, so here you do see there's some attribute is simple table, some attribute is error, some attribute is error in. So each one of the attribute you need to build you need to assign with these different attribute grammar. Okay, and it actually has a algorithm to generate it. Okay, has an algorithm to generate it. So anyway, the algorithm try to decorate the whole tree, and then eventually this different attribute for that calculator program become this. Okay, some of them are S attribute button up. Some of them are actually up down with a subtotal type. Okay, going through the whole tree. So the whole syntax tree become this. Okay, and some of them are synthesized attribute, some of them are L attribute. So eventually your syntax tree with the decorative grammar, attribute grammar is like this. Okay, and then if you want to, okay, so here we do know about the syntax tree like this. So if you want to build a recursive descent parser, that actually is right here. We do have an example, and that will build the whole parser, including the declaration. Okay, so this one is a whole guide to write a parser, and it's very detailed, a lot of things to cover. Okay, so this portion I don't have time to go into the detail. It will take hours, maybe a whole day to talk about it. Okay, so here we just have this. We have an example. Okay, we have an example for writing this one, and then go into the detail for every single rule, how to generate the parser. Okay, so this portion I don't have time to go over. So after the section 13, okay, it's a detailed implementation of the what we talked about here before. Okay, the whole thing, the definite guide. This one is a detailed guide for using Python to build the whole parser. Is that okay? But I don't have time to go over here. This is really too much. You have to look at the code, tracing the code for it. Okay, and we do have the code downloadable from our course. Okay, if you cannot download it, let me know. Okay, we do have the code downloadable from the video from our website, and this is too much. Okay, I don't have time to come over here. Okay, any questions so far? Sorry, today we probably need to finish here. Okay.
I have a question about the syntax tree.
Yes.
Do we build the tree? So can we use like a binary tree?
Binary tree depend on your grammar, right? Your syntax tree cannot be binary. The so-called binary tree is that you always have two nodes. You always has this, right? But actually we don't know how many subturn it is, so may not be. Usually it's not binary tree. Is it?
It would be best to use the trie tree that we built.
Trie tree is possible, yes. Yeah, it's a trie tree actually is good for simple table. Okay, but your evaluation definitely have to depend on how many turn, subturn. It may or may not be binary tree. It usually may have multiple branches. Okay, so may not be banana tree. It's just a tree. It's just a generic tree. Okay. Any question? And the whole parcel, we don't have time to go over. Okay, it's really big. Okay, it's actually Python code. We take too long. And here, just go through the basic idea. Okay, some detail you need to go through. Okay. And we don't expect you to be able to build a super big language, okay? So if, for example, if the term project, you work on something like AC controller, right? Smart AC controller. So you do have your house, okay, whatever house you have, right? You do have thermal sensor, a temperature sensor, right? Can sense temperature. You do have a smart sensor here, okay? Smart monitor here. So basically, you need to set a schedule, say Monday morning, 8 o'clock, turn on the heater, okay? So you do have a program here, right? And then this monitor control the AC on your rooftop heater. That's a certain heater. And your AC here outside the door with a fan. Okay? So you do have a language that actually say similar to assembly language that control your thermal sensor, your AC and your heater. You do have this assembly, okay? So actually turn on AC, okay? So AC will turn on, okay, or shut down AC, whatever. These are your assembly. If you are able to compile your schedule to this assembly, that is also a translator, right? Is that okay? Don't need to be super complicated, like Lisp translating to assembly. I don't need you to do that in your term project. Even this one is okay. Does that make sense? Okay. Any question? Even this one is okay. Most code to English is okay. Up to you, okay? The language, the project is something you need to be creative. Okay. So maybe this assembler only 10 instructions. That's fine. I don't expect you to do super big program. Okay. As long as you know you are applying the knowledge you learn from here to the project, that should be fine. Okay. So the example we give you in the textbook and also slides is super huge. Only one simple calculator language can be very complicated. Okay. So we don't expect you to give me a language that actually has 300 instructions like Intel processor, and then tons of the rule, maybe 300 rules that you cannot finish within reasonable time. Okay, we don't expect that. Okay, we just expect you to find a simple language, maybe something like this calculator language, 10 rules, 15 rules, and then you build a 3 possible compiler. That would be good. Okay, is that okay? Don't try too hard. Try too hard, you can never finish. Okay? And which part you need to use, that's up to you, okay? You want to do recursive descent parser, or you want to build any Python or whatever, just try, okay, just try. We don't judge your program for completeness or correctness, but we do want to evaluate your creativity. Is that okay? Because we notice it's only a term project. We don't expect you to write a super compiler for parallel processing using the C++ and then load down to a media processor. Okay, that's too much. That's too much. It doesn't make sense. Okay, it doesn't make sense to do a project like that. You will probably take 2 years to finish it, and not a single person's job. That's not the purpose of doing this. The purpose of doing the term project is to see your creativity, and then you try to translate some language to another. That would be good enough. Okay. So just be creative. Okay. Any question? No? Okay, no other question if we are done today, okay? And let me know if you have more question. Come back next week or give me email, okay? Okay, that's it for today. Thank you. Bye now.
All right, thank you.
Bye-bye.